All right. Yeah. All right, then. We're going to start the last kind of portion of this section. I don't know if I told you this already, but I think instead of giving you like an in-class quiz on this, I'm going to give you a take-home quiz over the weekend. So you can take it home and work through it and bring it back on Monday. And then on Monday, we'll start the last part of the semester. So that's a chance to get a really good test score, if you know what I mean. All right, here is finally our opportunity to understand where are the electrons actually in all these structures. Because when we looked at atomic structure, we talked about orbitals. When we did Lewis structures, the orbitals seemed to just go away and we were putting dots everywhere. Now we have to see, can we merge the two theories? Can we take what we've learned with Lewis and see how the orbitals fit in? So it turns out that when I first started teaching this, one of the accidentally greatest puns that I did not intend happened. And it's been haunting me ever since. So today, after the lesson, I can use my pun and we can all laugh at me. It's the greatest pun of my life. And it was an accident. So what we're going to talk about here are called hybridization, or just hybrid orbitals. So let's start with a simple statement. Atomic orbitals, the ones we're used to, can mix to form new hybrid orbitals. What does the word hybrid mean to you here? Just in general, what does the word hybrid suggest?
Two things at once.
A mix, two things at once, a blend. So there are a couple of important conditions to understand how these things mix. First of all, you will get as many hybrid orbitals as orbitals you put in. So the number of hybrid orbitals that you're going to get is equal to the number of atomic orbitals that you mix. That will make more sense once I show you examples. And the other thing is that there's a simple way without even having to sweat at all, how to figure out what the hybrid orbitals are. But I want you to know what that means too, not just how to, I could teach you in 2 minutes, oh, just do this and you got it. So I'm going to show you that, but then I'm going to try to explain what it all looks like and means. Here's the thing. Every energy level has one s orbital and 3 p orbitals in the atomic sense. So these are atomic orbitals. We've seen their shapes before. And I'm going to put this on the side. An s orbital in 3 dimensions has like a spherical shape, right? The p orbitals, of which there are 3 in a given energy level, have this kind of, whatever you want to call that, a dumbbell or a peanut shape. And it turns out that for the expanded octets, we need more orbitals. Remember I said we have d orbitals we can play with? It turns out for the purposes of this class, we're going to need 2 of the d orbitals that are close in energy level to our valence electrons that we normally talk about in the s and p subshells. And those d orbitals typically have, again, a particular shape, kind of like a 4-leaf clover. Now, if we tried to explain the bonding in molecules with those orbitals, it would be extremely inefficient. Here's why. In the hybrid kind of concept, and in the really, we're kind of dogging around something called molecular orbital theory, but in this concept, the way that bonds form is based on what we could call orbital overlap. Meaning 2 orbitals can slide together and become 1. And when they overlap like that, what that means is that becomes the region where the electrons hang out. So when we've been writing like a Lewis structure, and we say, oh look, here's water, and you know, it's got these bonds and they're sharing these electrons. What's really going on here, there's got to be some kind of orbital that the electrons are actually in. But they're not sitting in regular atomic orbitals. Because if we tried to make those bonds, the overlap is not efficient. So what actually happens is as a bond is forming, the orbitals on some of the atoms can actually shift their position and direction so that the overlapping is a lot more efficient. So I'm going to show you how you can determine that real easy, and then I'm going to try to draw some pictures and some simulations to help you visualize it. All right, first and foremost, let me start with the simplest type of hybrid orbital. Let's go to this side. So, if you take an s orbital and mix it with a p orbital, what you're basically doing is you're taking what looks like a sphere and what looks like this dumbbell or peanut shape, and you're overlapping them. Now when you do that, in some sense they're going to add together kind of like waves. In the sense that, this is going to be weird, but I'm going to try to make this work, color code. This one looks good to me. Okay. So what I want you to think about, the reason why I'm color coding this is, do you remember when we were doing waves, and if a wave was kind of overlapping in coherently or together, they would add up to a bigger wave? But if they were going opposite each other, they would cancel out. I remember that? So think of these orbital color codes kind of like, if we think of this red as kind of like a moving in one direction, like positive, then we can think of the green one as a negative. And again, not literally like charge, but it's like positive is up, negative is down. So like if positive overlaps with positive here, it's going to build up to a stronger wave, let's say. But if positive and negative overlap, they're going to cancel out a bit. So here's what I'm getting at. When I overlap this s and p orbital like this and mix them together, where the things are the same, in this case the way I've drawn it, right? The red circle and the red side of the p orbital are going to add up and make it stronger. But the red part and the green part are going to cancel out and make it weaker. This might be confusing, but let me just show you once. I'm not going to do this over and over. I'll just show you once so you can see what we're trying to show. When these overlap, it's going to swell to one side because it overlaps constructively there, but it's going to shrink on the other side. So we're going to get a deformed looking orbital. That's what I mean by hybrid. Now you're looking at that like this. What are you talking? That makes no sense. Watch this. I can prove it with paint. Here is a can of white paint. Here is a can of red paint. If I mix them together, what do I get?
Pink.
How much? How many cans?
2 cans.
Right. I would get 2 cans of pink, right? So the color in this case indicates the concept of a hybrid. Pink is a hybridization of red and white. It's a blend. The reason why I get 2 cans is because I mix 2 cans. So what I'm getting at here, if I start mixing atomic orbitals, I get as many out as I put in, but they change just like the color of paint changes when I mix it, because the way the orbitals overlap causes them to shift more in one direction than the other. Okay? You don't have to understand that any more than that. I'm just trying to give you context. Here's how we actually identify the hybrids, and then I'll show you what they all look like. Surprise! Spoiler alert! They're basically going to look like that, fat on one side, small on the other, and they're going to point toward the direction that Vesper predicts. It all kind of connects together really easily. So let's start with, what do we call that overlap? S and P, wait for it, will make two sp orbitals. Atomic hybrid. I put two orbitals in, I get two identical new orbitals out. They're actually called sp hybrids. Take one s and mix it with two p orbitals. How many am I going to get out? Three orbitals in. How many come out? Three. Very good. But now they're going to be called something else. Can you guess what we're going to name these hybrids? Close. We just combine it and call it sp2 because there's two of them. Same idea. What if we add all of these? What if we had all the p's in with the s? How many orbitals will we get now?
4 sp3.
4 sp3 orbitals, right? And if we want to go to hypervalence, we can start adding in d's. If I add one s, 3 p's, and a d orbital, what do you think we get out there? Come on, you can say it. How many?
5.
5. And what will they be called? You guessed it, sp3d. Are you starting to see any connection between this and what we've done with Vesper yet? 2 orbitals, 3, 4, 5. What is this starting to look like on our Vesper chart? It rhymes with schmomains. Domains. Isn't the first Vesper family have 2 domains? The next family has 3 domains, 4 domains, 5 domains. We got one more to go, right? S, all 3 p's mix, and then 2 d's mix. And we put 6 in, and we get 6 orbitals out. What we're showing here is that the blending of the atomic orbitals creates new sets of hybrid orbitals that shift in the direction and shape that they point to maximize the overlap and make the bond the strongest it can be. That's what's driving this. Now, how do I recognize these orbitals in actual molecules? I'm glad you asked. This is the Lewis structure for methane. How many domains are around it? How many domains are on the carbon, sorry? 4. If I have 4 electron domains, I'm going to need 4 orbitals to put those electrons in. If I need 4 orbitals and I'm going to hybridize, I have to mix 4. So we're always going to go from S toward D in this direction. That's why you can think of this as the hybrid palette. And just in this direction, take as many as you need to mix to make the number of orbitals that are required. So because this has 4 domains, it needs 4 orbitals. That means I'm going to mix S, P, 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 and therefore we can point to this carbon and say that this carbon is sp3 hybridized. Why does that make a difference to its bonding? Well, if it was not hybridized, here's what we would have. The carbon would have its 2s valence electrons, and then it would have the p valence electrons. And when you try to bond that to hydrogen, a hydrogen would come in with its 1s and try to overlap over here somewhere, over here somewhere, over here. It's just not efficient. That's how it would look if we stayed with atomic unhybridized orbitals. Here's what it looks like when it's hybridized. The carbon's in the center, but now the orbitals have a fat pointy end out in one direction, in that direction, in that direction, and in that direction. I'm leaving off the little tails on the back end that I drew here because they don't really have any significance. They just make it look messier. But can you kind of tell the way these are pointing now? Are they pointing at 90 degrees? These sp3 hybrid orbitals, of which there are 4, are pointing to the corners of a tetrahedron. In other words, just like Vesper tells us the shape of this should be tetrahedral, it also kind of rings together with the hybrid orbital theory that our hybrids are going to follow that same geometry. So they're going to actually point in the tetrahedral direction. And then, when I want to connect the hydrogens 1s electron orbitals can overlap very efficiently here to form the bonds that we're talking about. Hydrogen. Whew. Let me pause there for a second. Yeah?
So like on those molecule things, the orbitals are kind of like just like the sticks in between the electrons.
Yeah, and the thing is, this doesn't really show them as orbitals. This gets closer, right, to showing it that form. But yeah, that's what they are. These are the orbitals in which the electron pairs we've been talking about sit. That's right. But here's the beauty of it. It looks complicated at first, right? But if I put up one chart, you're going to see everything you've already learned is connected to this. You just have to learn how to label it S's and P's. Check it out. There is a simple and direct correspondence that you can see between Vesper shape and hybrid orbitals in this chart. Two-domain molecule needs two hybrid orbitals. So we hybridize S and P, and we call them sp hybridized. But they point in the exact same direction that Vesper says they should. They're linear to each other. Let me show you what that looks like a little more clearly. Cool. Oh, that's not good. Well, I got too many things open, I can't. I think this will show it better. Okay, so watch how I'm going to actually hybridize S and P.
Taking an s orbit with one of p orbitals generates two equivalent sp hybrid orbitals.
Do you see how they change direction a little bit and they blend into those two new orbitals?
Atomic orbitals that are hybridized. The set of two sp hybrid orbitals has a linear arrangement. The angle between the orbitals is 180 degrees.
So this sounds just like Vesper, except instead of saying domains now, we're saying hybrid orbitals. All we're adding to the picture of your understanding is that real quantum theory calculations from the atomic orbitals we learned last chapter can be used to actually predict and calculate these hybrid orbitals and give the right results. They tell us the right angles, they tell us the right bond, everything. So ultimately, when you mix two, you get two, and they follow the same geometric patterns as Vesper does. So what do you think sp2 is going to look like by that argument? Which way will the sp2 orbitals be directed? Question. It's three domains. What's the shape of a three-domain structure? Trigonal planar. Watch this.
Mixing an s orbit with two of the orbitals generate the equivalent sp2 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybridized.
You see how they
sp2
now
hybrid
point toward the
orbitals
corners
has a
of the triangle?
planar arrangement. The angles between the orbitals are 120 degrees.
Sounds just like Vesper to me. It's just we're putting orbitals in. What do you think the sp3 orbitals arrange in terms of space, the shape, whatever? What would you say there? How many orbitals is sp3? That's 4 domains worth. What's the shape of a 4-domain structure? And so the new orbitals point tetrahedrally.
P orbitals generates 4 equivalent sp3 hybrid orbitals. Note that the number of hybrid orbitals produced is equal to the number of atomic orbitals that are hybrid orbitals as a tetrahedral arrangement. The angles between the orbitals are...
Again, tetrahedrally arranged, but these are 4 unique orbitals that point in the directions of the tetrahedron off the central atom when this atom is sp3 hybridized. Let's go to the next extent. Let's add the d orbital in. Oh look, 5 made 5. Oh look, they're going to point along the 5-domain shape, which is trigonal bipyramidal. And of course, we can finish it off with the 6-domain arrangement, which is sp3d2. Gives us 6 identical ones. that point along the octahedral direction. So my point here is, as complicated as it may sound at first, there's a direct correspondence between hybrid orbitals and what Vesper already tells us about the shapes of molecules. They agree very well in this case. Okay, it's time to tell you the greatest pun of all time. This was a pure accident. So I was trying to explain, you understand that if I mix 1 can of red paint and 1 can of pink paint, I get a pretty, red and white, I get a pretty deep pink. But what if I mix 1 can of red and 3 cans of white? Isn't it a lighter pink? Isn't it gonna average more toward what there's more of? So I was trying to explain to the class, and just to give you more realistic looking images here of these orbitals. Let me open this link here. I have it open already, but all right, check this out. So this is an sp orbital in one direction. See what I'm talking about, how it looks kind of fat? And one end's just kind of pointy? Well, I was trying to explain to the class, they don't all have the exact same shape. Because when you mix S and P, they have different shapes, and you know the blend is going to be somewhere in between. So I said, well, if you mix S and P, it's 50-50. And that's why an sp orbital is kind of fat like that on one side. But what if I go sp2? It's going to have a similar shape, but you see how the back end is a little bigger and it's not quite as fat? That's because we had 2 p orbitals that have that more extended shape. So again, I was trying to make this point and they weren't getting it. So guys, look at it like this. When I look at sp orbitals, it's 50-50, right? It has more S-ness, more of that spherical shape because of the S-ness. Then I said, but the sp3 orbitals are kind of pointier, a little thinner, because we're mixing 3p orbitals with 1 s orbital. And I said, it doesn't have more S-ness, it has more, and guess what I said? And I said that, just like that, because here's what I was thinking in my head, right? I was thinking S-ness, to imply it's more round, and of course, the other one. So I said it. And everybody started laughing. I said, what? They're like, didn't you hear that? I was like, what did I say? They're like, say it again. I was like, what, that? And I said it, like, they made me say it like 6 times before I realized what I was saying. Everybody was dying. I'm just like clueless. And that's my great job.
Can we get a recreation?
So these have more S-ness, and these have more P-ness. But at the time, I didn't know what I was saying. Anyway. Whew! So, let's look at one more thing here. I just want to really focus on getting the idea, and then we can point to any molecule and instantly get it. So, and let's just go there because I'm probably out of time. I'm going to put a Lewis structure on the board. We're going to point to a bunch of different atoms, and you tell me what hybrid orbitals you think are in them. All you have to do is count the domains and then put the right number of orbitals together to call it that hybrid. Look at this carbon. If I ask you what's the hybridization there, what do you tell me? Just count the attachments or the domains?
4 sp3.
This is just sp3. You don't have to put the 4 in front. There's 4 of them. So we say the carbon's sp3 hybridized, where there's 4 different hybrid orbitals here. What about this carbon?
sp2.
Yeah. How did you know that?
It's connected to 3.
1, oh, I forgot 2, 3 domains, right? So it's sp2 hybridized. What about the oxygen over here? Look carefully. Lone pairs are domains. How many domains? Which one? How many of what?
SP3.
Oh, there's only 1, 2, 3.
Oh, SP3, not D.
Yeah, this is sp3. When is the only time we're going to have d orbitals in the mix? When we have an expanded octet, basically, yeah, that's right. Because we need those extra orbitals. So that's the essence of what you have to be able to tell from using hybrids. Is that bad? Pretty easy, right? That part. That's why I'm not going to make you draw all the weird pictures. I just wanted to give you some kind of context. Now, we said that bonding represents the overlap of orbitals. So that's easy to understand if they just slide together. So like, for example, if I'm looking at carbon monoxide, it's got a triple bond between carbon and oxygen. One of the bonds is easy to explain because we know these are sp hybridized, both of them, because they both have only 2 domains. So if I take the carbon and draw the sp orbitals on it, one of them would point this way, and one of them would point that way. So that's an sp orbital, that's an sp orbital on this carbon. The second carbon in the molecule is, or sorry, the oxygen in the molecule is in the same boat. It's got one this way. Oh, look, they're overlapping. And it's got one this way. With this model, we can explain part of the bonding already. The overlap of these sp hybrid orbitals in this position, this overlap creates a bond. There's a special name for this type of bond. This is called a sigma bond. And usually we use the Greek letter lowercase sigma. This occurs when orbitals overlap end to end. So, like this. Here's 2, oh, this is paper. I gotta use my hands. These are 2 orbitals, watch this. That's sigma overlap. They literally slide together. It's very efficient and very strong when they do that. So that explains one of the bonds, but this is a triple bond. It also explains the lone pairs. Because you see this guy over here?
I can put a lone pair here. I can put a lone pair here.
The question is, how do we get the second and third bond? Where does that come from? Am I out of time? How much?
You have 3 minutes.
Okay, I can say this in 3 and reinforce it tomorrow, but that takes all the homework off your plate tonight. There's not going to be any homework tonight. All right, we got to do it in class tomorrow. Watch carefully. Don't freak out. But remember, carbon also has p electrons that we haven't dealt with. It has a p orbital in this direction, and it has another p orbital kind of in and out of the board that we haven't used. Remember, we mixed an s and a p, but that left 2 more p's to work with, right? But these orbitals can't overlap this way, can they? But could they overlap this way? Side by side? They're parallel. They're next to each other. Could they overlap sideways? They can. That's called a pi bond. A pi bond, like the word, which uses the actual Greek letter pi. That's when we have side by side overlap of orbitals. And so we can literally get the orbitals to kind of jump together on the sides here, and on these sides here. The pi bonds are the double and triple extra bonds. So when you see a molecule that has a triple bond, you know that one of them is always the sigma type, and the extra bonds are always pi bonds. I'm going to stop there, and we'll start there tomorrow, and just ignore all the assignments for tonight. Let's finish the lesson tomorrow, and then we'll go from there. I'm also going to have a molecular modeling lab, because we're basically done when this is over with this lesson tomorrow, and then we're just going to go right into the lab, and then go from there. So, anywho, now it's time.
Yes.
Okay, friends. Homework. Crap. That was very big.
Hey, Queen.
Homework questions from you first.
You like that?
You want me to go over anything on the paper from yesterday?
Say hi to the-
Or
say hi to the-
general questions?
So when it's a molecule,
Yeah.
you said how you have to look at bond polarity and the shape. right?
Yes, for polarity.
But what if they like contradict each other?
Give me an example.
Like,
It is?
well, I can't think of it off the top of my head. But like, what if the bonds are polar, but like the shape is symmetrical?
Then it's a non-polar bond. As long as they balance out, that's okay.
So the shape like weighs more than like.
The overall symmetry does, because to answer your question more directly, let's say we had the carbonate ion, which by the way is a resonance structure. I'm going to draw it kind of closer to the true geometry. It's trigonoplanar. But
And I didn't recognize the last name.
let's remember that this is a resonance structure. But the key point here is this is trigonoplanar. Okay? So it's symmetrical by shape. It's got oxygen in every corner, so it's symmetrical by element. So this ion is nonpolar. But if I break the element symmetry, meaning I put an element here that's different, it doesn't pull the same as these, it just became polar. Because I cannot get them to balance now because they're not all the same. So on the other hand, if we looked at something like sulfur dioxide, which is bent, the elements are the same elements, right? So it's symmetrical that way, but it's because it's at an angle, it can't balance itself out. So this molecule is polar. So you have to look at both cases, both parts. Is it symmetrically arranged, both in shape and in the way the elements are distributed? If that's true, it's non-polar.
Okay, for CO3, since it's double bonded, doesn't that like make it shorter, changing the magnitude of the dipole?
In this case,
No, for CO2. Or
well,
CO3.
it's not double bonded.
Oh,
It's
is
a
it?
resonance structure. One way we could kind of
Oh,
visualize
that's
it, just to make it look like all the bonds are equivalent, remember these are all 1.5 bond order. So there's not a short and a long. That's the whole point of resonance. It's trying to describe something that's hard to describe with words. That's why the resonance structures average out when they're equivalent to the truer picture.
Okay.
Can you explain O3?
Yeah. So ozone has 18 valence electrons. So if we just start by bonding the atoms, I always say satisfy the outer ones first, okay? Leave the middle for the end. All right, all 18 have gone in. But I'm not done because why? Yeah, we're missing the octet, right? But we can't add more, we've used them all. So now we have to make a multiple bond, double bond somewhere. I could do it from this side, and I'd be done with the Lewis structure. But because they could have been on both sides equivalently, technically I should show it both ways, because again, this is the idea of resonance. So neither of these is the right picture. The right picture is the blend of the two, where each of these bonds is 1.5 order, basically. Oh crap, nobody caught me on that, I made that mistake there. I put 1.5, what should I put?
1 1/3.
Thank you.
I was gonna ask that.
My fault. Because, right, it's, that last bond split 3 ways. So 1/3 goes each way, so 3. Sorry about that. Yeah, so, you see what I did here? So anytime you have equivalent resonance structures, you have to include them all and understand that their average is the reality.
And you wanted like the dashed line and then like how long they would be each, or would you want both of them?
No, this is the way Lewis does it. This is kind of like a mod after the fact that people just did to try to make it more clear that it was really a blended one picture thing that we were trying to show in 2 pictures. So this kind of makes it more visually pleasing than this. The problem here is it's hard to follow the octet rule because how do you count this? You know, it's like, so this is clunkier, but it's how it's shown in the Lewis method. Yeah.
Is O3 non-polar?
That's a great question. Now, let's look at this. Because of this way this is shaped, we have to look at, this is A, X2, E1. That gives us a bent shape. This is one of the rare cases where even though it's all the same element, the angle causes it to be slightly polar. Because if you think about what it would look like, there's a couple things going on here, right? Like, you've got basically 2 atoms kind of working against one in a way. So it will pull the electrons more down and make this side of the molecule just a little more negative than this side because of it. And that's moderated by the fact that this lone pair is in here, so that it gets more complicated than I'm making it. But that's essentially why I would say this is slightly polar. Yeah?
Can you CL
Yeah, that's a tricky one. I threw that in as a curveball because it's what's called a free radical. Free radicals are molecules that have unpaired electrons, and they're very reactive. So these are the things that basically when we're doing our digestion and our metabolism and the chemicals reactions in our bodies, these free radicals kind of pop in and out of existence. But the problem is they're so reactive is if they hit something important like a DNA structure, they can react with it immediately and wreck it. That's a big cause of cancer. So free radicals, one way that we try to moderate that cancer is because we take something called antioxidants, because they become like the targets and they can kind of sop off that stuff and make it less likely to harm ourselves. I don't know if you knew this, but you have cancer cells in you all the time. It's just your body just knocks them out. The only time you get cancer is when it gets out of control and your body can't, eliminate them. Did I answer your question? I forgot. That's what it was. Okay, so obviously the problem here is it's going to have an odd number of electrons, right? 7 and 12. So there's 19 valence electrons. So interestingly, I just put this in to see what you'd come up with, how you'd mess with it. But you still follow the same basic procedure, right? You attach the atoms first, satisfy the outer atoms next, and then try with what you have left to satisfy the middle. But you see, you fall short. That's unavoidable. You can't do anything about it. But you can draw it as different resonance structures. In other words, we have to decide: is it better to put the one electron here, or on one of the oxygens? So those also count as resonance structures because they're different arrangements, right? Well, formal charge should be able to tell us which is better. Let me go back to both pictures. Obviously, the oxygen on either side having the single electron is going to be basically the same calculation of formal charge. So let's just try it here and here. So this formal charge, I'm just going to say them if you want me to show you how I did it. Ask. On this oxygen, it's -1. This one's, the chlorine's +1, and this is -1. No, that can't be right. Oh, there's only one electron. This one's 0, sorry. Because 1, 2, 3, 4, 5, 6. So that's one arrangement. This arrangement would make this one -1, this one -1, and this would be 1, 2, 3, 4, 5, +2. So what seems like the better place to put the single electron? This one, right? So again, it was a twist on what we'd learned, and I just wanted to see if you could extend that in any way.
Remind me how you get the number above.
I'm just counting. Well, this number.
Yeah.
I'm sorry. So I look at the normal valence electrons when it's by itself.
Yeah. Well, I know that the bond is 1, or like 1 each.
Oh yeah. So
I just don't remember that order.
yeah. So 1, 2, 3, 4, 5, 6 is how many it has to itself, and it splits this with the other guy, so it gets 1 and 1.
7, yeah, but so it's the number it actually has minus the number how many in there.
It's the number it normally has from the periodic
Yeah.
table minus what's in the molecule picture that.
Yeah. Okay.
Good.
Yeah.
Yeah.
Propane,
Yeah. I
it
got you.
is non-polar.
Right. For this, and this is why I kind of made this point yesterday, anytime you have a pure hydrocarbon, meaning nothing but carbon and hydrogen in the molecule, it's automatically nonpolar. No matter what the shape or structure is, they're nonpolar. So that's how we know that, just automatically. Did you want to know the Lewis structure and all that too, or is that?
No, I already got it.
Any other questions before we go on? Yeah. Yeah. That one is nicely arranged that way because it's really kind of giving you a hint to what's attached to what. So when you see it this group this way, it's telling me that probably you're going to have this representing this chunk. That's going to connect to another carbon. They're going to connect to the oxygens, and that's going to connect. You see the OH? So I'm kind of following how it's already laid out. Now to fill out the rest of it, we have to count electrons and be sure. 4, 7, 8, 12 is 24 valence electrons, I think. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh, so close, but the carbon didn't work. Darn, I wish there was a way to fix that.
Double bond.
Voila. Okay, I didn't end up collecting this today. I'll get it tomorrow in case you need to look at it some more, but I also ran out of time from the other class, so I want to give you the same chance. We're going to turn our attention now So starting the last topic of this unit, section. Yes, sir.
Will we get a lab?
I'll explain. What?
Lab.
Yeah, so tomorrow we're gonna do like a modeling lab,
Okay.
so with molecular model, more kind of study. Yeah,
Notebooks?
no, this is just a packet, or paper, just. The test, I decided to give you on this part of it, remember, we're actually doing 2 units in one. So the midpoint, on Friday, I'm gonna hand you a take-home test. This is a great opportunity for you to get a good test score coming for the end of the semester. So you get it Friday, you turn it in Monday, that's it. And you can work on it together, obviously it's meant, you know, I'm not gonna protect a take-home test, but I strongly encourage you to actually try to figure things out and understand them, because you're gonna see a lot of those similar concepts on the actual exam you take in class before, you know, the final, the one that's on the facility. So it's an opportunity, this is how I would tell you to do it. I would work through it, see what I know, look up the things I don't know and study those and make sure I get them. And then I'd verify everything and I'd try to get 100. Why wouldn't you, right? So that's what I would do. Here's what I wouldn't do. I wouldn't go find the smart kid, well, can I see yours? And then just copy it. I mean, you get a good score, but then you're gonna fail the test at the other. So it's not cost effective to do that. I'm not gonna police it, because I think you're smart enough to know if you're trying to do well, that you're gonna do it right. And then you're gonna verify it to make sure. Anyway, enough about me. Yeah.
Is the final not over the whole unit?
It's over the full semester.
Mine was okay.
The final exam is over the semester.
Is it 2 different semester
Good.
tests? Unit tests?
You went to gym?
No.
I've stopped going
Yes.
to gym. This one.
So, the one I'm giving you Friday is just a midpoint. We used to give a whole separate exam for both Unit 5 and 6. But they were so connected, we decided to give a midpoint kind of check, and then a full-blown exam that covers both. So there'll be a test before the final, one last test, other than this one. A take-home exam.
Did you say that like 500 BC? Actually, the test on Monday that we go again.
No, I meant, when you're working through it over the weekend, try to solve the problems, use your notes, whatever, at some point, and then check with each other, verify. I'm saying, like, try it first. Don't just look up all the answers. You just waste
Yeah,
time.
Michael.
How you get?
He's a kid. I like him.
Okay, let's get into, oh, go ahead.
Not you.
You think so?
We'll see.
He'd be bigger than that though.
Okay, ready? Over there? All right, now,
Sorry.
this is gonna be hard to follow if you don't follow it, like everything else.
I'm gonna follow.
All right, we're gonna look at what are called hybrid orbitals.
Hold on.
So I know based on how it went the last class that that I'm not gonna finish everything without racing, so I wanna take my time and make sure you understand each part, and then finish tomorrow's meeting. Let's start with the concept of what hybrid means. What does hybrid mean?
Multiple.
What? Okay, it could be 2 or
Like
more.
a mix.
Mix, right? Like a mix or a blend, right? So for example, if I have a can of white paint, right, and I mix it with a can of pink paint. Oh, I'm sorry, I meant to say red paint. I'm ahead of myself. What will I get? But think about this now. What I'm about to say is really important. How many cans of paint will I get?
2.
The same amount.
Yes. 2, meaning if we compare by volume. I don't mean like they're all in one can, I mean it's the same volume. So you're literally gonna get 2 hybrid cans of paint. What do I mean when I say hybrid? What's hybridized here? Yeah, but I mean, what property was hybridized? The color. The color, right? And what if I had instead added 2 cans of white paint?
More light.
It would just be a lighter pink, right? So it would still be a hybrid, but it would be a different hybrid, and it would be a different shape. Here's what I'm getting at. Just like cans of paint, the atomic orbitals that we learned about in the last unit, the S, the P, the D, and the F, let's review what they look like. So these are atomic orbitals. As we learn them, based on the hydrogen atom and all the other elements were kind of similar. But the ones that we knew, or tried to know, had certain shapes. Here are the 3 that we kind of studied. I'm just going to draw them without the axes. The S orbital was like a spherical shaped cloud, if you recall. The P orbitals had this kind of almost dumbbell shape. And I'm just drawing one of each so you can see the shapes. And then the d orbitals, most of them had a shape that looked like a four-leaf clover. And again, these clouds, or atomic orbitals, were these regions where the electrons hang out. So
What about F?
we're not even going to need them, so I'm leaving them out. But you're right, they're there too.
Okay.
They kind of an 8-leaf clover,
Okay.
like if you doubled the d. Kind of.
Yeah.
But here's my point. I'm going to just show you something. I'm going to try to explain what's going on. If I wanted to bond two atoms, okay, here's what we've been saying. Covalent bonds are electrons being shared.
Right.
And we've been drawing these weird things with sticks. So I'll do methane real quick. Like that, right, to represent the electron pairs that they're sharing. And we say, okay, the nuclei are both sharing the electron. But the thing is, our atomic orbital theory comes from quantum theory, which is kind of the thing right now. So these Lewis pictures came before all that. And they were an attempt to figure out how, to explain bonding before the quantum theory was all in place. Long story short, after the fact, we have to now go back and say, what happened to all the orbitals? What do the orbitals look like here? Because if we believe atoms have orbitals, then when they unite, it seems to make sense that the molecules are going to have orbitals too. But they're going to change. That's the key point. Just like mixing paint changes the color, mixing these orbitals changes their shape and the direction they point. That's the key. So I'm going to show you one example of how that kind of works, just to clear your mind of like what I'm trying to show. And then after that, you don't have to worry about how I did that. Just kind of see if it makes sense first. So let's take one s orbital, which is a sphere, and one p orbital that are in the same atom, and let's overlap them. Now, before I tell you what happens when I mix them, let me remind you about waves, because we did something like this when we talked about waves. Do you remember when I was showing you how waves kind of overlap with each other? If you have one wave that's kind of moving this way up and down, let's, for the sake of argument, call the up ones positive and the down ones negative, just to distinguish their phase. Their phase means like where are they in the cycle, right? These are in opposite positions. Now imagine I brought a second wave to overlap with the first one, and it was exactly lined up. The pluses are lined up and the minuses are lined up. What new wave would I have created? What will it look like when they're together like that? Will it change anything? It will. It'll make an even bigger wave.
Oh.
That's what we call constructive interference, right?
Yeah.
On the other hand, if we took the original wave and this time we overlapped the second wave out of phase, meaning when one was high, one was low, what would happen there? What would the sum of these two waves do? They'd cancel out, wouldn't they? In other words, we called this destructive interference. So it would be like the wave's not there right there, because they're balancing each other, canceling out. The way we mix the orbitals is kind of like that. If we understand that the s orbital, if we think of it as like a plus for a moment, just to kind of all line up with the wave concept there, then the p orbital has a plus side and a minus side, okay? Kind of like our waves have an up and a down. Now think about if I overlap these two orbitals, what might happen?
And cancel out as well.
Exactly. So if I call this positive, meaning the circle, and then half the p orbital is positive and half is negative, what will it look like? You said it's going to kind of swell in one side and shrink in the other, right? So it turns out that here I have one s orbital and one p orbital blending together, and here's what's going to end up making. A fat end where they overlap positively, and a little tiny end where they overlap negatively against each other. Yeah.
Do we like assume that if it's positive, that positive kind of like takes away from the negative, or is it just like,
Yes.
Okay.
In other words, the probability of the electron being there starts to shrink,
It's shrinks over.
and where they overlap, the same way, that's where the probability grows. The electrons are basically going to spend more time here than here. Now, let me explain why this is happening, though. Because this can't be the only answer, right? Because if this was the only answer, I'd only get one new orbital. I have to get two orbitals. When I mix two, I gotta get two. So it turns out that this p orbital could have also been drawn the other way. So the other possibility is that we get the same exact thing, but pointing in the opposite direction. These two orbitals look a lot different than these two, don't they? One here is a perfect sphere, and one is like pointing in opposite directions equally. This created something that really swells one way and then really swells the other way. These are hybrid orbitals, just like mixing the paint made new color. Here, mixing the orbitals made new shapes. And remember, these shapes mean something. They're the probabilities of the electrons. What's the point of all this? Well, first of all, there's a name for this type of hybrid orbital. It's really complicated. What did I mix in here?
Carbon.
No, what kind of orbitals?
S&Ps.
The hybrids are called sp hybrid orbitals. Wow, how complicated. Now, I don't need you to understand this any better than that just idea that it happens. You don't ever have to do this in a test or anything like that. I wanted to show you that when I'm mixing the orbitals, there's a reason why they change which way they're pointing, and they change where the kind of where they swell toward, because that's going to affect how they bond to other atoms. Yeah.
Do you know which side's gonna be positive and negative?
It's both. In other words, both possibilities
But
have to be accounted for.
when we draw, we have to draw. all-
No, you don't have to do any of that. That's what I'm saying. I wanted to give you some understanding of what's going on, but after that, what I'm going to show you that you have to do is painfully easy. Yeah.
How do we know that it gets bigger on one side and smaller on the other?
How do we know
Yeah.
from what I did, or how do we know in the broader sense?
Broader sense.
Quantum calculations.
Okay.
I'm just going to say that every time you ask me a hard question because that'll
So boring.
What?
It's so boring.
I
You
know.
can't
Well,
do
I'm
that.
sorry, I just can't do that for
This
you.
is interesting. I like this.
Okay,
Oh,
yeah.
when he says a simple answer?
So how does that lead to like a different SP?
How does it, what part?
How does it lead to like a different, like that new orbital because of positive?
Oh, because where positive and positive act together, they reinforce each other. So they make that part bigger. But where positive and negative overlap, they take away from each other, so they make that part smaller. Yeah.
And why is it sometimes positive and sometimes negative? Like what does it change?
Again, that's much more complicated than I can tell, but that's why I tried to use this model just to give you a sense of what's going on. It's not really like waves canceling, but it acts similarly. That's why that model is kind of conceivable, I think, to us. That's why I'm saying that. But now I can show you a very simple model on the screen that you're going to understand is directly connected to what you already know. So we're really just modifying VSEPR a little bit here to understand what we're going to get.
Yeah.
So check this out. So let's do the SP first.
It's okay.
So there's an S and a P, right? We blend them together, and two new orbitals are created with different shapes. And now those two orbitals are what we're going to bond with to a next atom. Why would we do this? Like, why does the atom's orbitals change this way? Here's why. When we've been saying covalent bonding is sharing electrons, we had this kind of just notion that two nuclei are just attracting the electrons, right? But what this is saying is that for us to share electrons, what's really going to happen is the orbitals from one molecule's atoms are going to overlap with the other one. Orbital overlap is how we're going to try to understand what covalent bonding is. So the better they overlap, the better they're going to bond. Like if you take two spheres and glue them together, are they going to stick real good? Why not?
No surface area.
Yeah, they're gluing at like one point. But if you take two sheets of paper, two flat pieces of wood and glue the whole surface, isn't it going to stick real good? There's much better overlap, right? So look at this. When the molecules are forming, the orbitals are literally shifting so that they can overlap the best and make the strongest bond, thus releasing the most energy, thus making the most stable system. It would be like, well, I can't use that analogy because you wouldn't have seen it. Anyway.
No, say that.
Well, I was going to say, if you take like a magnet and put it under a piece of paper, and then you sprinkle iron filings on it, you would see a pattern that kind of looks like this, where the iron filings are following the magnetic field lines. And if you put one far away on the same paper, you get a similar looking thing, almost like you have two s orbitals. But as you push them toward each other, the shape of the pattern would change because of their interaction. And instead of looking like two separate things, what you would see is something that looked more like this, of the iron filing patterns, because the way the fields interact with each other. So what I'm saying is, just like two magnets with these field lines around them moving toward each other and redistributing how it looks, so do the atoms. Orbitals do that as they're coming together, because by skewing the electron density toward the right place, orbitals can overlap more efficiently and make a stronger bond. So that's really what this is about. Oh, was there a hand? Yeah.
For when you combine S and P,
Uh-huh.
how come you get two and then you combine them, or what's?
Say again?
Like you get two different.
Two orbitals, yeah.
Two orbitals.
Two go in,
then
two
you
come out.
You combine them, like this.
Oh, why are they combined?
Yeah.
Because they're two orbitals on the same atom. Like this
So-
atom, whatever atom we were playing with here, let's say it was carbon. And let's just look at its outer shell. Normally we would show it like this, right?
Yeah.
The outer shell of carbons. But what happens here is by kicking up this extra electron and blending the orbitals, we can create 4 new orbitals that are called sp3 orbitals, which I'm going to explain in a minute, all that have the same energy as each other. And now we have 4 bonding locations that are pointing toward a tetrahedron corner. In other words, just like we would predict if we were doing Vesper and we were looking at something that had 4 domains.
Totally made sense. Like I
You didn't get anything
no,
I
I didn't get
said.
it.
Let me get there, because your
Okay.
questions are good, but I have to build up to what you're asking.
Alright.
All right, let's go through the whole
That's
list.
Superman.
Watch the whole list, and then I'm going to show you how simple you can make this, or I can make it. SP2, what do you think I'm going to blend?
SP and two.
1 S
Two P.
and 2 P's. How many orbitals am I going to get?
Three.
So again, they're going to skew, they're going to blend in a way that points at those angles and skews the shape. You recognize the shape?
Oh, it's a trigonal
Yes. 3 orbitals, right? Now watch what happens if I go sp3. What shape do you think we're going to get?
Tetrahedron.
Very good.
Or
In other words, we're going to get 4 orbitals that, when we look at them from a common center, are pointing toward the tetrahedron corners. In other words, that's where the orbitals are going that are going to be used for bonding.
Is it
If-
the same angle all around?
It's all 109.5. It's a tetrahedral ring. If I do sp3d, that's why I need, remember how we said we can get like third row elements and later to have more than an octet?
Yeah.
We said because there's more orbitals. Here's how they both play in. Now we have a 4th orbital in there, a 5th orbital, sorry, and we get 5. 5 out. Again, they all kind of look the same, but these are not very realistic images. I'll show you a more realistic one, and then I'll show you the greatest joke I ever had, but it was an accident. And then our octahedral shape comes from adding 2 Ds into the mix. The commonality is every time I mix more orbitals, I get more. Every time I mix more, they end up at different shapes. What a strange coincidence. They all end up pointing toward the Vesper shapes.
It's not a coincidence.
Here's why. This one chart pretty much summarizes it perfectly. So here we have our Vesper domain groups. Here are the primary shapes of those domains that we've been studying. Bond angles. Here are the hybrid orbitals that associate. When there's 2 domains, I need 2 hybrid orbitals. So I mix 2 atomic orbitals, an S and a P. How do I know which ones to mix? Here's the palette that you're going to use. S, P, 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 D, D. In this order, you take as many from there as you need from left to right to figure out what orbitals you're going to make, which hybrids. So like, for example, if I was doing, give me a molecule.
Hydrogen.
Give me a better one.
Oxygen.
Carbonate.
Good. We'll do this one. Wait, oh, this is the one we had a minute ago, right?
2.
Yes.
Let's put this one up. All right, check this out. It's this simple. The part that you have to be able to do is part of the part. You'll have to finish it. How many attachments are on this carbon?
4.
So doesn't this have 4 domains here?
Yeah.
So 4 domains need 4 orbitals.
Mm-hmm.
1, 2, 3, 4. This carbon is sp3 hybridized. Meaning, if I was to take that carbon and want to show where the electron densities are, there'd be a fat one going that way, that way, that way, and that way along the corners of the tetrahedron. I'm not going to show the little tails because they're pretty inconsequential. But we have now 4 sp3 orbitals. And just to make a quick example of what I mean by orbital overlap, because I'm almost out of time, each of the hydrogens around here just has the 1s electron, right? And an s orbital is a sphere. So to show how the hydrogen bonds here, the hydrogen's 1s orbital can overlap pretty efficiently with the sp3 hybrid. And that's where the electrons go. So what we're calling a bond here, this pair of electrons, is really the result of the overlap of these orbitals. And the hybridization effect makes the overlap more efficient. That's why it happens. Now I'm going to tell you really quickly my great joke that happened by mistake. So I was trying to show the class how the hybrids looked, like in terms of their shape more carefully. So I said, look at this one, and I showed them the sp orbital. You see how fat it looks on one side?
Yeah.
And how skinny it looks on the other side? That's because sp orbitals are 50% s, which is round, and 50% p, which is lengthy, right? So it's going to have 50% fat, 50% thin. Then I said, well, look at what happens if I go to sp3. They have a similar idea, but you see how it's not quite as skewed as the other one? So I was trying to explain to them, see, this has sp3 has 3 p's in it, and s only 1. So I was trying to explain sp orbitals are fatter because they have more s-ness. Meaning s-ness, like more of the s, right? And the sp3 orbitals are skinnier because they have more, and I said it. And I said it and they all started laughing. I'm like, what's so funny? And they made me say it 6 times before I what I was saying. All I was saying was this.
No, I can't.
Yes, I can. P. Ness. Have a good day. No homework tonight.
Yay.
Cancel everything. I'll catch up with you tomorrow. Sorry, and so if you look on the screen, just to quickly summarize the hybrid orbitals and how they connect to Vesper, I'm going to just do this really fast. Then I'm going to show you what you actually have to be able to do with this, so it's clear. And I'm going to give you something to practice on to make sure you understood it. In the second half of class, the lab that we're going to do is just kind of reviewing all the concepts at once. But I thought it would be more interesting instead of just keep looking at simple little molecules. I built a bunch of like everyday like important molecules for you, and I made like pictures like for each one so that you can actually like analyze each molecule, figure out what it is, look at Vesper components within it, look at polarity, things like that. So I wanted to do it in a more kind of big scale thing so you'd see this is real. It's not just these dinky little molecules that we can analyze. So I just thought it'd be more interesting that way. But it's just more practice. Tomorrow we can finish it, and or whatever you want to ask me. We'll look at some of the problem set again, and then I'm just giving you the take-home test. If you want to work on it in class tomorrow, that's fine. Or you just take it home and work on it. Bring it back Monday. Done. Tomorrow's Friday. All right. So again, the hybridization concept. In order for us to figure out what's the hybridization of the orbitals in a molecule, we just have to see how many domains we need. So let's just pick a molecule. Let's do CH4, which if you do the Lewis structure first, how many domains does it have? 4. 4 domains means we need 4 orbitals, and that means we have to mix 4. Remember, the mixing is S, P, 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 D, D in that order. So what would the hybrid orbitals be called in this carbon? sp3. So we will get 4 identical sp3 orbitals. Now I'm going to show you how that works. So that means I need to put an s orbital, and then 1, 2, 3 p orbitals. Now I'm going to hybridize them. These are the 4 new orbitals that we created. They're all identical. And what shape do you see them adopting? Tetrahedral. So this molecule is AX4, which is tetrahedral from Vesper. But now we can see that instead of imagining just dots floating nowhere between atoms, we now have orbitals in which the electrons that bond can go. They just look different, their energy's a little different, and they're shaped and pointing in different directions. But that's the essence of it. So far, so good? All right, let's do another related, similar molecule, and then we'll show how the overlap works to create the bonds. Next one. Ow. I was never good at electric shocks. Okay. How about we do ethylene, which looks something like this. Okay? If I asked you what's the hybrid orbitals in this carbon, what would you tell me? 1, 2, 3 domains. sp2. If you're not sure how we're getting that, you should ask. So how many orbitals am I going to generate as a result of mixing these? How many? 3. Correct. 1 s goes in, 2 p's go in, and then we hybridize, and we end up with what geometry of the orbitals? Yeah, because around this atom it's AX3. We know from Vesper that's trigonal planar. And again, the hybrid orbitals just point along the same direction that Vesper predicts. The only thing you really need to understand is that the orbitals are changing shape in such a way as to maximize the bonding. And that's happening because as they extend in specific directions, they can overlap with the orbitals of other atoms from other, or other atoms better, I should say. All right, one more like this. Let's do ethine, also known as acetylene, used in torches, like the kind that for cutting and welding in auto shop. If I pointed to this carbon, what hybrid orbitals would you expect it to have? Say again? So just SP, right? You mean 2 of them? You're good. So this is going to be SP hybridized. What does that look like? Well, take an S, take 1 P, mix them, and you get these 2 orbitals. Now, this is AX2 around this carbon. What geometry does Vesper tell us AX2 is? Linear. Do you notice that our 2 orbitals are pointing along a linear direction? So all of this connects. If we have to go to higher valences, like for expanded octets, that's when we throw the d orbitals in. So let's look at something like xenon difluoride. Let's figure this one out. What is that, 22 valence electrons? 8 and 14. So let's see if I can trick you with this one. Not done yet. That's 16, 17, 18, 19, 20, 21, 22. Now, what is the hybridization on this one? I know what you're probably wondering. What are you wondering? What do I think you're wondering? Because everyone I did so far didn't have any lone pairs. So what do you think? What do I think you're wondering? Why are you not answering right away? Boom. What do you do with the lone pairs? They are also counted as domains. There are places the electrons have to go, so they need orbitals. 1, 2, 3, 4, 5. How do I build hybrid orbitals with 5? What would we call those? SP3D, correct. And if we build that, we would need the S, all three p orbitals, and a d orbital. Then we hybridize. Does that shape look familiar? Nope, not quite. It's the trigonal bipyramidal one. So based on Vesper, the domains are trigonal bipyramidal here. I'm just going to abbreviate. Because even the lone pairs need domains to go into them. Okay? And then, we don't probably have to do another molecule, but let's just add one more d orbital in there and finish the pattern. What's the last one I'm going to be able to build that I need to build? sp3, what? D2. So I need two d orbitals. And of course, as you might expect, we're going to get 6 identical orbitals that are hybridized and pointing along the octahedral geometry. So there's just a direct correspondence between Vesper and these hybrid orbitals. All right. Any questions so far? So far I think you have adopted the skill that I can point to an atom in a bonded molecule and you can tell me just based on how it's attached or what's on it, what the hybrid orbitals are. Does that sound right? That you can do that now? You'll get practice and know for sure in a minute. So let's look at how these hybrid orbitals then overlap to create sigma and pi bonds. We're going to kind of go through the same simple basic molecules here. Okay? So, first of all, ethane has this Lewis structure. All single bonds. Okay? Before we even go on, it's going to show us this in a minute. Let's see if you can do it. What's the hybridization on this carbon? What hybrid orbitals will this carbon have? sp3 is correct. What about this carbon? Also sp3. They both have 4 direct domains. Okay? Now, watch what happens next. First, there's a talking guy behind this. We show those sp3 orbitals. So each carbon has now converted its s and p atomic orbitals into these sp3 orbitals. Is that clear how this is just shown? Okay? Watch what happens next. They're still talking in the back. I can't make it stop talking until it's done. Oh, yeah, so they're showing you now the electrons, right? Because the carbon has 4 valence electrons. Now there's 1 in each of these hybrid orbitals. All right, next. What you just saw happen there is called a sigma bond. The 2 orbitals that overlap end to end form a very good overlap, and anytime that happens, you're going to get sigma bonding. That is the stronger type. A sigma bond is the more efficient type of overlap and the stronger type of bond. Okay? So, how do we explain where all the hydrogens go? Well, each hydrogen has its 1s orbital with 1 electron. That overlaps with these hybrid orbitals on the carbons, producing sigma bonds all around. And now we have the molecule. Something interesting about a sigma bond, particularly a single bond, is that the molecule can rotate. So, in other words, if you notice what they're showing, that's actually important to the behavior. Because in later molecules, when there's double or triple bonds, that rotation isn't allowed. And it causes a different kind of isomerism that's really important in chemistry. But anyway, that just explained the C2H6 molecule with hybrid orbitals and overlapping. All the bonds were sigma. So as I'm doing this, I'm going to show you everything we just said. In this molecule, where everything was single bonded, both carbons were sp3 hybridized, and every bond, every single bond you see there was a sigma bond. Sigma, 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 sigma. Because some of the questions you'll be asked about this is how many sigma and pi bonds are in the molecule. In this case, there's 7 sigma bonds because of the way they overlap. No pi bonds. All right, let's move on to the next molecule and look at how we deal with the double bonding. So first we start again with the Lewis structure, as always, when we're doing covalent bonding. This one has a double bond. Before we go on, what are the hybrid orbitals on this carbon? sp2. This one? Also sp2. So let's look at how those hybrids form. There's our sp2 hybrid orbitals on each carbon, adopting the trigonal planar geometry that associates with 3 domains. Those hybrid orbitals each have 1 electron in them. But wait a minute. Doesn't carbon have 4 valence electrons? I only see 3. Why are we missing one? Well, funny you should ask. When you look at carbon, its configuration is 1s2, 2s2, 2p, 2. But when we start hybridizing it, if we only take an s and 2p orbitals and hybridize those, isn't there still a p orbital left over? So now we're going to have the second energy level, but it will have sp2 orbitals. It will have 3 of those, and it will still have 1 more p orbital that we haven't used. This electron pairing prevents more bonds from forming. So what's going to happen, instead of this electron sitting here, now that we have all these equivalent orbitals, we're going to get 1 in each, and then the 4th electron goes there. So the reason why you don't see 4 electrons yet is we haven't accounted for that last unused p orbital. Watch what happens, because this is the key to bonding the double bond. So first of all, we get sigma bonding, as before, by the direct end-to-end overlap of 2 orbitals. There's your electron pair. There's the orbital picture of it overlapping. That's a sigma bond between the carbons. Again, the hydrogens can bond to each end by overlapping their 1s with the sp2 orbital of the carbons. The only thing we have not figured out is how do we get the double bond? Where's the second bond coming from? And the answer to that is it's coming from the p orbitals that we haven't used yet. Check it out. So, as I said before, there's still 2 p orbitals, 1 on this carbon and 1 on this carbon. And they're going to be perpendicular to the plane, so they're going to be parallel to each other. If I click next, there. See how they look? Oh, they went too fast. So the 2 p orbitals that were once like this can overlap side by side. So we get electron density above and below. This is called a pi bond. With a pi bond, we have parallel side-by-side orbitals overlapping sideways. Okay? Again, just to make this hopefully more clear, end-to-end overlap is sigma bonding. That's preferred. That's the stronger type of bonding. That's what happens when it can. But if there's leftover orbitals side by side, they can overlap to some degree and form what's called the pi bond. The pi bond will be, again, have a cloud above and below the point, or I should say the line connecting the nuclei of this molecule. So that's how a pi bond forms. Now that we know that, if we go back to the actual molecular picture, let me draw a little bit more in the right shape, might as well, since it's trigonal planar. Okay, now, here's what you need to be able to do. If I point to this carbon, you tell me it's what hybridized? sp2. This one? sp2. Every bond starts as sigma. So every bond that you have has a sigma always. First. The second bond in the double was formed by that side-by-side overlap. That's the pi bond. So every time there's a double bond, there's going to be a sigma and 1 pi. Doesn't matter which is which, I'm just trying to label it so you can clarify, okay? So anytime there's a double bond, it's a sigma and a pi. The sigma comes from the direct overlap of them sliding together. The pi comes from the side-by-side overlap. Okay? Are we still good? Or is there any questions? All right, one more. And then I'll show you a little bit more pretty pictures. Then we can practice. Acetylene has a triple bond. We've already stated it's going to be sp hybridized, which gives linear geometry of the orbitals as well as of the molecule. Again, we can get a sigma bond overlap here for one of the bonds. And then the hydrogens are going to attach by sigma overlap on the ends. Here comes that. Now this time, because we're looking at sp orbitals, there's 2 unused p orbitals on each carbon. So I've only had to mix one s and one p for this one to get the hybrids. And that's why there's 2 p orbitals left over. So what you saw me do a minute ago, side by side, can happen twice now. What does that look like? Well, it sort of looks like this. Sort of looks like this. The main thing I want you to notice is that this up and down pair is one pi bond, and then there's one front and back that's the other pi bond. It's like, think of it like this. A sigma bond is a corn dog, and a pi bond's more like a hot dog. The bun. Bun in a hot dog is top and bottom, right? But a corn dog just wraps right around the That didn't help, did it? What if I do this? Sigma, pi. Sigma, pi. Nothing? All right, well, she liked it. Sorority. Okay. I'm going to show you the pi bonds with one more pretty picture, just so it's a little more clear. So let me jump into this one. I like this one because watch what I can do. I can show the Lewis structure. I can show the sp2 orbitals on carbon 1. I can show the hybrid orbitals on carbon 2. I can then show the sigma bonds. And now you can see the p orbitals before they overlap. These are the unused p orbitals just waiting to be used. How do they actually end up overlapping? Like this. Let me get rid of the yeah, where is the, you see something that's, oh, there it is. I just want it to stop spinning! Okay, so what I really want you to notice, do you see these yellow balls? Those were the atomic p orbitals before they overlap. The red region now shows you how they overlap side by side and create electron density above and below. This is a pi bonding orbital here. The sigma bond is the one right in the middle. Is that cool or not? Is that like something you can... Okay, so let's do this now. Let's see if you can actually apply any of this. I'll do a couple with you, and then you'll do the rest. There you go. One, two. Did you guys turn in the other thing I thought I asked you for? Some of you did. Okay, this is in half. You guys don't have the assignment for the other day, or did you all turn it? I just don't see like there's a lot of them.
Are you done?
Okay. Yeah. One more. Let me put this up on the old screen here so I can do the first one with you, and you get the hang of what this is about. Number one lesson, do not take the pictures literally when you're looking at the angles. You have to apply VSEPR. Otherwise, you will not get the right answers. Okay? Look, it screams 90 degrees. It's not 90 degrees. So the way I laid this out for you, carbon 1, carbon blah, blah, blah. First I'm asking for hybridization on each carbon. Ready, rapid fire, go. Carbon 1, Hala. sp3, carbon 2, sp2, carbon 3, sp2, a second voice is heard. Carbon 4, sp, a third voice is heard. Carbon 5, sp, multiple voices at once, oh my god. That wasn't so bad. What about the bond angles? Bond angle 1. How are we supposed to figure it out if I'm telling you it's not just a picture? What? Yes. Because of the AX4, it's based on the tetrahedral geometry, and tetrahedron geometry means the angle is 109.5. Applying that same logic, what would you call angle 2 in the real molecule? Yeah, so what's that angle in terminal planars? 120, right? And then angle 3? 180. So again, we can apply VSEPR point by point throughout the molecule and see what the shape implication is and then the angle from that. The last question, which I'm going to lose all my placement there, is just asking for sigma and pi bonds in the molecule. This is the easiest one now. Once you see it again, you're going to know it perfectly. Watch. All you have to do is literally go everywhere there's a bond, covalent bond, and write sigma. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And anywhere there's a multiple bond, the extra ones are all pi's. Here's a pi, here's 2 pi's, if you like. That's 3 pi bonds total. That's the extent of the skill you need in this. That's kind of what I was trying to teach you yesterday, but for some reason I was all over the map. I got too excited. Okay, you guys can try to finish the rest of these now. And then at the halfway point, meaning after the bell, we're going to start the little lab activity. Okay? I do intend to collect this. Like today. It shouldn't take that long. Okay, welcome to hybridization.